In this last example, what we're going to do just show is this idea of parameterizing a curve. There are different reasons for doing this. Again, we note that we have these rectangular or Cartesian functions. They don't have a flow or a direction to them, but by parameterizing or giving them a parameter, we actually can create a flow given a specific situation. And again, this might feel just like a cool math trick that we're doing. There's actually real applicable reasons to do this. But generally the basis is this. There's one way to do this. There's actually an infinite number of ways to parameterize this curve. When you actually do this, you'll probably have different reasons for a specific type of parameterization that you're trying to use. But the simplest in this case would be to describe x, that the function x of t is just t. So in this case, you say, well, x is defined by t as just being t right there. So you're basically doing a substitution for t in this situation, and then you can say that y of t equals 2t squared minus 5. And if we were given a domain restriction here, we'd have to realize that in our new parametric equations. Importantly here is the statement is that, and again I said, given a context, there might be different reasons for what to choose, especially for x of t. But I could choose really anything as long as what I choose as the expression for x doesn't change the domain. Now again, in this case, when I'm seeing this without a domain restriction, I'm expecting that since this is a quadratic, it's a polynomial, it has no domain restrictions. It's all real numbers from negative infinity to infinity. So as long as I define x of t to be an expression that it has that same domain, I shouldn't have any issues. So for instance, I could do something like define x of t to be t cubed plus 9. And then in the same vein as what I did right there, so I've described x in terms of this expression right here, this cubic. All I would need to do is take this expression and replace the x value with this expression right there. So y of t then would be 2 times t cubed plus 9 squared minus 5. And then this at this point is actually two parametric equations that work. Just because this is a squared and it's not too much work, I am a bit compelled to expand this and clean this up a little bit. This isn't really a huge deal, but just I'm feeling kind of anal and I want to do it. When I multiply this out, I'll get t to the 6 plus 18t cubed plus 81 minus 5. Distribute a 2 through here, and then make sure I take care of that minus 5 with the constant here to give me y of t equals 2t to the 6 plus 36t cubed. This gives me 162 minus 5 is a positive 157. And so again, this example is just setting up for when in the near future you might have a reason to parameterize a curve. Again, one of the reasons might be is that you want to give a certain direction. These x values change a bit in terms of t. This would change faster because your t value is cubed. But there could be an example not just to kind of speed up time or whatever this parameter value is, but maybe you want to go a certain way along the curve. You can use the trick of parameterization in order to do that.